Okay, so 4.3 is called Absolute Extrema, which can also be called Global Extrema. Global and absolute mean the same thing. So the idea or objective for this lesson is finding extrema guaranteed by the EBT and finding absolute extrema, different standards. So first, let's introduce another theorem. Extreme value theorem, which can be abbreviated EVT, and I would say for derivatives, just so you know. It says we have some conditions. So our function must be continuous. You can plug in all x values on the original, on the closed interval, same conditions as always. Then our function attains both an absolute max and an absolute minimum value at some numbers, some x numbers, on the closed interval. Okay, so the key here though is that it must be a closed interval. If it's not a closed interval, then you can read this note down here that it means that it might not apply. Okay, so it would not be guaranteed by the EBT. So to use this theorem, you just have to say f is continuous on the closed interval. And that's it. You can have more than one max and min, but that's it. Okay, so here's a visual. So as a reminder, we're looking at the interval from A to E, just because, and it's the closed interval. We know our function is continuous. We don't care if it's differentiable or not, but look, we have a few absolute, the overall lowest point, okay, is called the absolute minimum of the whole graph. You're looking at the y values. And then the overall highest point is right here. So absolute max, okay? Now, there are other local or within a small area. So like right here, if I just look in this little window, then that's going to be the highest point. So that's called a relative max. Notice this point is the overall highest point, and it's also called a relative max. Okay. So same thing here. This is in this little region, C has a relative minimum y value, but it's not the overall lowest y value. Okay. All right. And we can identify other things. So if we want to find the absolute extrema, first we would be given a function. So remember that extrema, I'll write a little note up here, but your max and min can only occur when you have a horizontal tangent line. So when your derivative equals 0. It's not going to be a max or min when your derivative is undefined, but it's a critical value. So step number 1 is to find critical values. Okay, remember that means when your derivative is equal to 0. Okay, I'll also put or undefined. It just usually doesn't happen there. So the number 2, you're going to make a table. And it really is one of those traditional XY tables. I'll write it down here. So include endpoints and critical. And then 3, compare y values. And it really is that. Okay. So did you know, this is a technicality, we call it AP semantics. So if a question wants to know where the absolute max or min occurs, it might say find the x value, it might say where, then your answer is going to be the x value. A lot of times though, it will just say what is the absolute max or min. So if it wants to know the absolute max or min value, then you're looking for a y value, okay? So here's an example. If a problem asks for the greatest speed, well, it would be 50 feet. That would be the y value, not that it occurred at t equals 3 seconds. So sometimes you might, you can get around this by saying a graph, or how about f of x has a max of 50, whatever it is, let's say meters per second at t equals. If this was a free response question and you weren't sure if you write the statement using this idea, you actually would get credit, okay? Because it's technically true. So I just kind of summarized it here as well, okay? So let's try our first example. Find the absolute max or min for each function on the given interval. So first thing is we want to find our critical values. So find our derivative. And these can be any kind of derivative. I did a polynomial and trig and then a few others, but I just mixed them up. So these all should be solved by hand, typically. So this derivative equal to 0, add 4, divide by 8, so 1/2, okay? And so remember, that is a critical, which is a possible max or min. We wouldn't know unless we did a sign chart, but it typically is going to be a local extrema. So I'm going to make a table, and then we're going to include our endpoints. I did forget to double check to make sure that this polynomial is continuous from 0 to 2, but it is. That would be too easy of a question if it wasn't. And then we also want to include our critical value. So then we're really just going to compare. The overall lowest value is the absolute min, and the overall highest value is the absolute max. We don't care if the others are local or not. So where are we at? So if I plug in 0, remember you're substituting this into the original equation. So if we plug in 0, we get 1. If we plug in 2, I always skip, I know. So 4 times 2 squared minus 4 times 2 plus 1. So 4, 16 minus 8 plus 1. So 8 plus 1 is 9. And then 1/2. This will take a little longer. So 4, 1/2 squared minus 4 times 1/2 plus 1. So 1 minus 2 plus 1. So 2 minus 2 is 0. So what I would say, and they just wanted to know, find the absolute max and min. So the overall highest, I would say there's an absolute max at x equals 2, absolute max of 9 at x equals 2. And we're going to write the overall lowest value is this. So there is an absolute min of 0 at x equals 1/2. Okay. All right, let's try some trig. So we're going to find our critical. Sine and cosine are both continuous, so the interval is fine. The derivative of sine is cosine. The derivative of cosine is negative sine. So our derivative is equal to cosine plus sine. Now, this is going to be a good trig review. You probably have not seen this since last year, okay, on this problem. And this shows up a lot as we keep going because we're doing more and more solving. So this problem will be good to watch. So we want to set this equal to 0. And move one of the terms to the other side. It does not matter which. Okay, so now I need to do some trig review. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. What this really says is, since this is negative and this sign is positive, it really means that you want sine and cosine to be opposite signs. So first we need to figure out which quadrants those are in. The good thing is we're only talking about 0, remember this is pi over 2, to pi. So I don't have to worry about these two because that would just give us more answers, okay? So I just have to see, is sine and cosine, are they opposite signs here or are they opposite signs in this quadrant, or neither? So as a review, remember it's all are positive here, all students, so sine is positive here. Take is positive, and then calculus, so cosine is positive. Okay, and so what it means is in this quadrant, I'm going to write it on the graph, it means that sine is positive and cosine is positive. In this quadrant, sine is positive and cosine is negative. Just in case our domain would be from 0 to 2 pi, let's go over this. So sine is, well, tangent is positive. So tangent, you have to remember, is sine over cosine. So if it's positive, it means that they're both positive, except we're going sine is the y value and x is the left value. So it's either they're both positive or they're both negative. So if we're in this quadrant, you have to know, well, cosine is x, so that's negative, and sine is the y value. So what it means is that in the third quadrant, sine is negative and cosine is negative. In the last quadrant, cosine is positive, and so sine is negative. Okay, so they're opposite signs in quadrant 4, and they're opposite signs in quadrant 2. Okay, so now we need to figure out what the actual angle is. So on our table, we know we have 0 and we have pi, but we need to find the angle where this is true. So we already know it's going to be in quadrant 2. So I'm going to draw in a little reference triangle. I need them to be the same number, but just opposite signs. So remember, you had 2 triangle choices. You had 45, 45, 90, which was 1, 1, root 2. And then the 30, 60 was 1, root 3, and 2. So if I need sine, which is opposite over hypotenuse, and cosine, which is adjacent over hypotenuse, we need them to be the same number because it says they're equal. Well, opposite over hypotenuse is 1 over root 2, and cosine adjacent 1 over root 2. So we know we're looking at a 45-degree reference angle. So this is 45. So remember, we start at 0, and that angle of rotation is this real angle. So all the way is 180, so 180 minus 45 is 135 degrees. Convert that to radians. These both divide by 45, so goes in there 3 times, goes in there 4, so 3 pi over 4. Now, on your chart, if you don't like the degrees, remember you can always write it in radians. If you don't like radians, write it in degrees. So this is 0 degrees, 135 degrees, and 180 degrees. That's your choice. On the AP exam, all the answers will be in radians though, so please get used to converting. Now we need to find the y values. So we found the critical value. There was only one using some review trig, and now we need to do some more trig so we can actually find y values. Okay, so our original is right here, and I'm going to write it down here. So sine minus cosine. So we get y equals sine minus cosine. So if I plug in 0, we get sine of 0 minus cosine of 0. So we want to remember our waves. So sine and cosine. So the sine of 0 is 0, and cosine of 0 is 1. So 0 minus 1 is negative 1. I'm going to jump to pi. So the sine of pi minus the cosine of pi. So sine of pi is also 0. The cosine of pi is negative 1. So 0 minus negative 1 is positive 1. So the hardest one will be this because we had to use our triangles, but that's okay. So our sides are 1, 1, root 2, and put your signs. We went to the left, so it's negative 1. We went up, and the hypotenuse is always positive. So we want the sine of 135 minus the cosine of 135. So sine, you're going to use this reference triangle. Sine is opposite over hypotenuse minus adjacent over hypotenuse. So opposite over hypotenuse. We'll worry about rationalizing if we need to. And adjacent is negative 1 over root 2. So negative 1, when the denominators are the same, we can add the numerators. So 1 plus 1 is 2 over root 2. You don't have to rationalize if this was a free response. If this was multiple choice, you just be flexible. If they did, you have to think that 2 is the same as root 2 times root 2. So then these would reduce. Root 2 is bigger than 1. So we do want to reduce that because we're trying to see the highest and lowest y value without a calculator. So to recap, our overall highest value, this would be our max, and this would be our min. Okay. All right, let's try another 2 different types of functions. So we have a quotient rule and a natural log rule of some ease. So find our derivative. We get quotient rule, low, d high, minus high, d low, all over low squared. Our denominator, if we set this equal to 0 to see what is undefined, we subtract 1, we take the square root, and we don't work with imaginary numbers. So what that means is that our function is never undefined, okay? So we can set our derivative equal to 0, which is really just our numerator. So I'm going to distribute to help solve. Minus 4x squared. We'll combine like terms and then solve. So I'll add 2x, divide by 2, and take the square root. Okay, so we're on an interval. We're going from -3 to +3. So both of these answers should be on our table for our critical values. So I use my endpoints and my critical values. Make a box here because the purple kind of gets lost, huh? Okay. And so remember, we're finding the y values and we want to plug it into the original. So if we plug in -3, we're going to get -6 over -3 squared is 9. 9 plus 1 is 10. So reduce and we get -3/5. Plug in -1. So -1 squared is 1. 1 plus 1 is 2. So reduce. +1 and 3. So 6 over 3 squared is 9. 9 plus 1 is 10. So we reduce. So we are looking at the overall highest value. So this is absolute max. And then the lowest value, it did not occur at an endpoint. Or the other ones. So yeah, on some of the other ones, they were at some endpoints and one was not an endpoint. On this example, neither one of them were endpoints, but you still need to check. All right, the last one of these examples, I just threw in a natural log as a review. So our derivative of natural log is, remember, 1 over u times the derivative of the inside. So our derivative is going to be 1 over the inside times the derivative of this inside, which is 2x. The derivative of x is 1. So once again, natural log has a restriction. They have it here, so -e to +e. And our denominator, since 1 plus x squared is never going to be negative, we had it on the last example, we know this is not going to be undefined, okay? The derivative. But you want to check. So set this equal to 0. I'm going to add 1 to this side. I multiply by the denominator. And so usually to solve this, this is where you get stuck, but you've got an x squared, an x, and a number, so you should be thinking factors. So get everything to one side and put it in order. So x squared, we're going to subtract 2x and then plus 1. This factors into AC method or trinomial. It's the same factor, and so if we solve, we get x equals 1. That's a critical number. So on our table, we've got -e positive e, and 1, which, remember, e is about 2.71, okay? Lots of review. So let's plug these in. All right, so we get e. The natural log of 1 plus negative e squared is going to be e squared minus e. Minus negative e, so plus e. So this is saying e to what power gives you 1 plus e? Well, we don't know. So I'm going to write this here. I ran out of room. Okay. And if I plug in e, it's going to be the same thing, except it's going to be minus e. And then we're going to plug in 1. So the natural log of 1 plus 1 squared is 2 minus 1. Now, these are together, so we can't do 2 minus 1, so it's just the natural log of 2 minus 1. On this problem, because you're not supposed to know what natural logs are, you would have a calculator, okay? If it was a different natural log problem, you might be able to simplify this by hand, but these aren't properties, so you can't. So I'm going to make a table up here, and I'm going to type them in to find the actual decimals. I know I didn't tell you that, but sometimes you have to look at the problem. So natural log of 1 plus e squared plus e. So 4.845. If I do the same thing, but we want minus e, get negative 0.5913. We can chop that off, and then natural log of 2 minus 1. Negative 0.3068. So we can see this is our absolute max, and this one is our absolute min. So both endpoints. Okay. All right, the last question says, what is the smallest, so that means minimum, absolute minimum, slope? Okay. So what we really want to do is we want to minimize the slope. So the slope is the derivative. And this is the original curve. So if I want to minimize or maximize something, keep in mind that means you take its derivative, set it equal to 0. So for my slope, it's our derivative, which is the power rule. And if I want to minimize that, I actually want to take the derivative of slope. So we're going to call this y double prime, because we want to find the critical value of the slope values. Okay, the slope minimizes or maximizes the y values. When you take the derivative of slope, it minimizes or maximizes the slope values, and that's what they want. So our second derivative is 6x minus 6. So we're going to set this equal to 0. And we haven't done this before because we're like kind of putting all the concepts together now. And so then you start deciding, well, how do I do that? What does this mean? So that's why I talk you through it. X equals 1, okay? Now, what we know is that this is a polynomial, so there aren't any endpoints. And so if you only find one value, well, it can't be a max and a min. So if we only find one value, that would be the value where it's minimized. Does that make sense? Okay. We can't really check it because we don't have the curve. We'd have to get table of values, and that takes too much time. Now, this is where, though. So that's where the smallest slope occurs. But I want to know the actual slope value. So I want to know this when I plug it into the slope equation. Okay, so you need to know what derivative you're looking for. So when in doubt, set a derivative equal to 0. But then you need to know, well, where do I plug that back in to find what I want? So you have to know, what are you looking for? What's the equation find? And things like that. So if I plug in 1, so we'll just call this like y prime of 1, I would get 3 minus 6 plus 5. So 8. 8 minus 6 is 2. So 2 is the smallest slope. Okay? So we found an extrema. We just applied it to a different problem in a different way. Okay? So those problems are coming. I won't be able to predict what the AP wants to maximize or minimize, but it was kind of like optimization. Think of it that way. This process should seem pretty familiar because they are related. All right, go ahead and give your problems a try, and good luck.